All right, so we're going to be working on Chapter 6, Lesson 4, solving compound inequalities. So what we're going to learn about is solving compound inequalities containing the word and graphing the solution set, solving compound inequalities containing the word or and graphing the solution sets. So compound inequalities, the word compound meaning things working together, right? And so what we're going to be working on when solving compound inequalities is we're going to be working on inequalities that actually have two inequalities kind of built into one statement. So some vocabulary to keep track of is what is a compound inequality, what's an intersection, and what's a union. How are compound inequalities used in tax tables? So it says Richard Kelly is completing his income tax return. He uses the table to determine the amount he owes in federal income tax. So here's the income tax table. And this was in the year 2000. So basically, if your tax income is at least this amount but less than this amount, it puts you in a specific tax bracket, right? So if this is the tax bracket that we're looking at, and it says if we let C represent the amount of Mr. Kelly's income, his income is at least 41,350, and it is less than 41,400. This can be written as C is greater than or equal to 41,350 and less than 41,400. When considered together, this is the whole compound thing, these two inequalities form a compound inequality. This compound inequality can be written without using and in two ways. So if you were to look at where his income would be, right? So it's saying that C is greater than 41,350, but less than 41,400. So that would be this tax bracket here and there. And so that's what we talk about when we talk about income or compound inequalities. So we can write it as C is greater than or equal to this number, but less than this number. And the smaller number goes here, the greater number goes there. Same thing, we could flip it the other direction. We could say that 41,400 is greater than C, and C is greater than or equal to 41,350. If you notice, these two say the same thing. Typically, you will probably see it written like this, though. So kind of as a study tip is when you are reading math, the statement 41,350 less than or equal to C less than 41,400 can be read as 41,350 is less than or equal to C, which is less than 41,400. So just a little bit of how to read this. So inequalities containing and. A compound inequality containing and is true only if both inequalities are true. Thus, the graph of a compound inequality containing and is the intersection of the graphs of the two inequalities. In other words, the solution must be a solution of both inequalities. So the intersection can be found by graphing each inequality and then determining where the graphs overlap. So let's look at a problem. So this example is where graphs intersect. So it says graph the solution set of x is less than 3 and x is greater than or equal to negative 2. So our solutions have to be an intersection of these two graphs. So the first thing I would do would be to graph this one. So graphing x is less than 3, right? Here's my number line. All the numbers less than 3 work. It does not include 3, so that makes an open circle. Now next I'm going to graph x is greater than or equal to negative 2. So here my graph on the number line shows every number greater than 2, also equal to 2, hence why it's got a filled in closed circle at negative 2 because it can equal negative 2. And the intersection of these is where these two overlap. Well, this one goes this direction, this one goes this direction. So if you notice, they actually overlap in these numbers right here. So my answer, my solution set for these two would look like this. It would include all the numbers that are greater than or equal to negative 2 and less than 3. So all these numbers right in between here including -2, but not including 3. So this is the solution set. And so this is how the solution set would be written for this problem. For all x's, x would be greater than or equal to -2 and less than 3. Note that the graph of x is greater than or equal to -2 includes the point -2, and the graph of x is less than 3 does not include 3. So now let's solve and graph an intersection problem. So if it says solve -5 is less than x minus 4, which is less than 2, the graph of and then graph the solution set. So if you notice, I have two inequalities here. So I can actually do this by just writing two inequality problems. So if I use this inequality, I can write it as -5 is less than x minus 4. And then I can also write this one. X minus 4 is less than 2. So basically, I took this inequality and wrote it as two separate inequalities. Now, this inequality becomes a really easy one to solve, right? How do you solve it? You would add 4 to both sides, right? Because you're trying to get the x by itself. So this zeroes out, and it would give me -1 on this side, x on this side. So this would tell me that x has to be greater than -1. And I also have to solve this one. So again, adding 4 to both sides. This zeroes out, leaves me with just an x, and on this side, 2 plus 4 is 6. So I get x is less than 6. So x has to be greater than -1, and x has to be less than 6. So the solution set is the intersection of the two graphs. So if I graph x is greater than -1, right, not including 1, and if I graph x is less than 6, right, not including 6, hence the open circles. So my graph for this whole solution set for this compound inequality is the intersection of these two graphs, right? Where do they overlap? And they overlap right in between -1 and +6. So this would be my graph, right? Open circle on both of them because it does not include -1 or 6. So all the numbers here satisfy this inequality right here, this compound inequality. Again, the solution set is written for all x's in this problem. X is greater than -1 and less than 6. So another study tip here when reading math, when solving problems involving inequalities, within is meant to be inclusive, right? So whenever I have less than or greater than or less than or equal to or greater than or equal to, it's inclusive. It includes that number. Between is meant to be exclusive, which means if you have a less than or greater than, right, not equal to, it's exclusive. It does not include those numbers. So now we're going to go ahead and talk about inequalities containing or. Another type of compound inequality contains the word or. A compound inequality containing or is true if one or more of the inequalities is true. The graph of a compound inequality containing or is the union of the graphs of two inequalities. In other words, the solution of the compound inequality is a solution of either inequality, not necessarily both. So an or means it only has to satisfy one and not necessarily both, not like an and inequality. So the union can be found by graphing each inequality. So let's look at an example. It says write and graph a compound inequality. So an airplane is experiencing heavy turbulence while flying at 30,000 feet. The control tower tells the pilot that he should increase his altitude to at least 33,000 feet or decrease his altitude to no more than 26,000 feet to avoid the turbulence. Write and graph a compound inequality that describes the altitude at which the airplane could fly. So again, when we're looking at this problem, it's asking us to examine it, right? So let's look at the words. It says the pilot has been told to fly at an altitude of at least 33,000 feet or no more than 26,000 feet. So basically, he's been told to go 30,000 feet or higher, 33,000 feet or higher, or 26,000 feet or lower. So basically, anything in between 33,000 and 26,000 is where they're going to encounter turbulence. So they either got to go above it or below it. So the variable, okay, we're going to let A be the plane's altitude, right? How high it is off the ground. So the plane's altitude is at least 33,000 feet, or the altitude is no more than 26,000 feet. So what does that look like as an inequality? A has to be greater than or equal to 33,000, or A has to be less than or equal to 26,000. So there's the inequality. So now we have to graph the solution set. So here's a graph of A is greater than or equal to 33,000, right? So here's 33,000 on the number line. Anything greater than that, it includes 33,000 because it can equal it. Then the other one is graphing A is less than or equal to 26,000. So here I have a closed circle including 26,000 and then anything less than that. So basically the plane has to either go above or below the turbulence. So my graph would be um, the union of these two things, right? So basically my graph would be both of these, right? Because the plane can either be lower than or equal to 26,000, or it could be equal to 33,000 or greater than, right? Anywhere would satisfy this compound inequality. It can't obviously be both, but it could be either on this side or this side. So this would be known as the union, right? I took these two graphs and combined them together. That is the union. So A must be greater than or equal to 33,000, or A must be less than or equal to 26,000. So example number 4 says solve and graph a union. So here I have solve negative 3h plus 4 is less than 19, or 7h minus 3 is greater than 18. So now let's go ahead and graph it and solve it. So again, I can write them obviously separately. So I'm going to start by just solving this one. So again, I'm solving for h. So I'm going to start by subtracting 4 from each side. And that's going to give me negative 3h is less than 15. Next step is to divide both sides by negative 3. Since I divided both sides by a negative, remember that you have to flip the inequality symbol. Anytime you multiply or divide both sides by a negative, that happens. So once I do that, I'll simplify it, right? I get h here, and then 15 divided by negative 3 is negative 5. So on this inequality, I know that h has to be greater than negative 5. Now let's go ahead and solve the other statement. Again, I'm going to start by trying to get the h by itself. So my first step will be to add 3 to both sides, right? These zero out. 18 plus 3 is 21. So 7h is greater than 21. Next step is to divide both sides by 7. And that would give me h is greater than 3. On this one, I divided both sides by a positive. That's why the inequality symbol stayed the same. So now I have my two inequalities. So h must be greater than negative 5, or h must be greater than 3. Now here's an interesting thing, right? The solution set is the union of these two graphs. So let's graph both of these, right? So I'm graphing this and this. So here's the graph for h is greater than negative 5. Here's the graph for h is greater than 3. Now if you notice, both of these graphs are headed off in the same direction. So if it has to satisfy this or this, right, as long as it's satisfied as one of them, it works, right? So the union of these two is if I were to combine both of these together, which would actually just be this one, because if a number is greater than 3, it's also going to be satisfy this one, right? So, and if it can satisfy either one of them, this is going to be my final graph because it's the union, right? I'm adding these two together, the union of these two. So that's how OR ones work. So notice that the graph of h is negative 5 contains every point on the graph of h is greater than 3. So the union of the graph is h is greater than negative 5. So that would be the solution set, right? Written like this. For all h's in this problem, h must be greater than negative 5. All right. Thank you guys for watching. If you guys have any questions, please ask.